In this paper, we delve into a comprehensive method that involves constructing prompt pairs, computing the mean difference, MD, vector, performing contrastive activation adjustment, CAA, evaluating steering effects, sourcing datasets, generating hallucination steering vectors, visualizing activations for contrastive dataset analysis, and examining the effect of CAA on behaviors. We begin by constructing prompt pairs, which are multiple-choice questions with answer options A and B. The positive and negative prompts contain the same question but end with different answer options, either A or B. We then compute the MD vector by taking the difference in the language model's internal activations at the position of the answer letter between all the positive and negative prompts. This vector represents the direction in the model's latent space that corresponds to the target behavior. Next, we perform CAA by adding the steering vector to every token position of the generated text after the end of the initial question or prompt. This shifts the language model's output distribution towards the desired behavior. We then evaluate the steering effects of CAA on held-out multiple-choice questions and open-ended generation. We assess the impact of CAA on model behavior and measure the change in behavior achieved by the steering vectors. We source datasets from Anthropic's Advanced AI Risk Model-Written Evals dataset and custom model-generated datasets using Claude 2 and GPT-4. These datasets contain multiple-choice questions with two contrasting answers that demonstrate the desired behavior or its opposite. We also generate hallucination steering vectors by crafting a dataset containing pairs of true and fictional statements about various topics. We use different strategies to elicit unprompted and contextually triggered hallucinations. Finally, we visualize activations for contrastive dataset analysis and examine how model activations for contrastive examples cluster in a low-dimensional space. We analyze whether the representations separate based on the target behavior and observe behavioral clustering in later layers, indicating higher-level representations of the behavior. We validate that the multiple-choice prompts elicit the target behaviors by examining how the model continues generation after answering either option A or B. We find that the model justifies its answer in the continuation text, demonstrating the effectiveness of the A-B format for producing steering vectors. We also test the effectiveness of CAA on open-ended generation beyond multiple-choice settings and assess the behavior influence on free-form answers to related open-ended questions.